Concept-based inquiry in mathematics. A grade 7 maths teacher walks into class on a Tuesday morning. She does not say hello. She does not open the textbook. She walks to the whiteboard. She writes one number. The number is 42. She underlines it once. She steps back. The class is staring at her. She turns around and says, "That is the answer. Your job today is to write the question." There is a moment of confused silence. Then a hand goes up. Then another. A boy at the back says, "What's 6 times 7?" A girl says, "What's 100 minus 58?" Someone says, "What is half of 84?" A small voice in the corner says, "How many cards in a deck plus the jokers times 4 divided by..." Wait, I'm working it out. In 4 minutes, the wall is covered in sticky notes. 25 questions, 30, 40. The teacher has not taught anything yet. She has not lectured. She has not written a formula. And the class has just produced the raw material for one of the most beautiful lessons in school mathematics. By the end of the period, these 12-year-olds will have discovered the meaning of a function. They will have discovered linearity. They will have rediscovered what mathematicians call slope. And they will have done it without anyone telling them. This is concept-based inquiry in mathematics. Pattern first, formula after, meaning before notation. The maths trap we all fell into. Let me tell you what almost certainly happened in your own school maths education, and in mine, and in the maths education of nearly every adult walking the planet right now. The teacher opened the textbook to page 117. The teacher said, "Today we are learning about linear functions." A linear function takes the form y equals mx plus c. Here is the formula. The teacher wrote y equals mmx plus c on the board. The teacher said, m is the slope, c is the y-intercept. Copy this into your notebook. Now we will do 12 practice problems. You copied the formula, you did the 12 problems, you got most of them right. You took the test on Friday, you passed, you walked out of the room. And here is the part nobody likes to say out loud. You never once understood what a function actually was. You substituted numbers into a formula somebody handed you. You produced answers. You earned the grade. And underneath all of that, the question of what mathematicians had really discovered, the question of why anyone in the history of human thought had bothered to invent this idea in the first place, that question was never asked and never answered. This is the maths trap. Teaching procedure before structure. Teaching the algorithm without the rule the algorithm is based on. Teaching the formula as a thing to memorize rather than as the summary of an insight. And here is the cost. A child who learns the formula can do the worksheet. A child who understands the structure can build a function for a phone plan, predict a savings balance, model a population, recognize when a relationship is not linear at all, and reach for a different tool. The first child has been trained. The second child has been taught. Concept-based inquiry in mathematics is the practice of teaching the second way, always. The flip. Here is the flip. In every concept-based maths lesson, the sequence is reversed. Traditional maths goes formula, example, practice, test. Concept-based inquiry, maths goes pattern, exploration, articulation, formula. Let me say that again because it is the heart of this chapter. In traditional maths, the teacher writes the rule on the board first and the children practice it. In CBI maths, the children produce the data first, articulate the pattern in their own words, and the formula appears at the end as a tidy summary of what they have already understood. The notation is the destination, not the starting point. We have a name for the kind of provocation that makes this work. We call them rich tasks or open middle problems. The provocation has more than one entry, more than one strategy, more than one form the answer can take. The provocation invites the child to think before it lets them calculate. So here is the move. In your next maths lesson, instead of writing the formula on the board, find the pattern that the formula summarizes. Then ask the children to look at the pattern. Wait longer. Let them say something, then let them refine it. Only when the rule has come out of their mouths do you write the formal notation. I am going to walk you through 4 worked examples. One from grade 1, one from grade 4, one from grade 6, one from grade 7. By the end, you will have a clear picture of how this looks at every age. And you will have lessons you could teach tomorrow. Worked example 1. Place value in grade 1. Picture a kindergarten or grade 1 classroom. The carpet is on the floor. The children are sitting on it. The teacher is holding up a clear glass jar. Inside the jar are 47 buttons. She shakes the jar. The buttons rattle. She says, "How many buttons are in this jar? Guess." The children call out numbers. 20, 50, 100. One says 4,000, and the teacher smiles and says, "Perhaps not." She writes the guesses on the board. Then she opens the jar and dumps the buttons in a heap on the carpet. She turns to one child and says, "Mona, can you count them for us? Quickly." Mona starts. 1, 2, 3, 4, 5, 6. By 18, she has lost track. She starts again. The class laughs gently. The teacher waits. She does not rescue. She says, "What is the problem? Why is this so hard? Talk to your partner for 1 minute. What would make this easier?" In 1 minute, the children invent things. Make piles. Count by twos. Use a tray. Put them in a line. The teacher writes down their ideas. Then she shows them 2 arrangements of the same 47 buttons. In the first arrangement, the buttons are in 4 cups of 10 with 7 loose. In the second arrangement, the buttons are in random piles of 3, 5, 8, 2, 9, and so on. She asks one question. Which arrangement is easier to count? Why? The children answer immediately, the one with tens, because we can go 10, 20, 30, 40 and add the extras. The teacher writes on the chart, equal groups make counting easier. Then she sends them to stations around the room. At each station is a different big number of small things. 23 pebbles, 36 paper clips, 52 cubes, 41 popcorn kernels. The children invent their own grouping strategy. Some try groups of 2. Some try groups of 5. Some try groups of 10. They count. They report back. Tens win. Tens are faster every time. By the end of the lesson, the children have not been told a single rule about place value. They have discovered with their own hands that mathematicians group in tens because tens are fast. And when the teacher writes 47 as 4 tens and 7 ones, the notation now means something. 4 tens and 7 ones is a description of what they did. It is not a rule they have to memorize. It is a label for an idea they already own. This is what concept-based inquiry looks like in a kindergarten maths lesson. The teacher creates a problem that hurts a little. The hurting is the point. From the hurt, the children invent the solution. The teacher names the solution at the end. There is a pitfall here, a big one. Do not rescue. When Mona gets to 18 and loses count, do not jump in with use tense. If you say it, you steal the discovery. The frustration is the lesson. Worked example 2. Fractions in grade 4. Now imagine a grade 4 classroom. The teacher walks in carrying paper circles. Lots of them. She projects a single image on the board. The image is 3 children. The image is 2 pizzas. The image has a single sentence above it. The sentence reads, "How will they share fairly?" She says, 3 friends are sharing 2 pizzas. No fighting allowed. It must be fair. In your group, use these paper circles. Show me your sharing plan. You have 4 minutes. The children fold, they cut, they argue, they show solutions. One group cuts each pizza into 3 slices and gives each child 2 slices. Another group cuts one pizza into 2 halves and one pizza into thirds and tries to make it work. A third group cuts both pizzas into 6 pieces each and gives each child 4 pieces. After 4 minutes, the teacher walks around. She does not say which solution is correct. She just looks. Then she puts 6 sharing situations on the board. 3 of them are yes, fair shares. 3 of them are no, unfair shares. In the yes list, 2 pizzas each, cut into 3 equal slices. Each child gets 2 slices. In the no list, 2 pizzas, 1 cut in half, 1 cut in 3. 3 children take whatever piece is left. She asks one question. What is true about the yes side that is missing on the no side? The children answer. Equal pieces, same size, fair cuts. The teacher writes on the board in big letters. When we share fairly, we cut into equal pieces. That is the deal. That is the promise of a fraction. Now she does something subtle and important. She does not write the word numerator. She does not write the word denominator. She writes this. The number on the bottom of a fraction is the number of equal pieces. The number on top is how many of those pieces we have. That is it. That is the entire definition, and it is built from the children's own observation. Then they explore 4 sharing missions. 4 children share 1 cake, 8 children share 2 cakes, 6 children share 4 chocolate bars, 3 children share 5 sandwiches. They sketch the share. They write the fraction. They compare. At the end, the teacher asks a question that opens the next lesson. Mission 1 and Mission 2 gave different fractions, 1/4 and 2/8. But the share is the same. How can that be? She does not answer. She leaves it hanging. The seed of equivalent fractions is planted. Next lesson will harvest it. Notice what is missing from this lesson. There was no rule about flipping the fraction, no formula, no procedure. The children walked out, understanding that a fraction is the name of a fair share. The denominator is a promise of equal pieces. That understanding is the foundation. Every fraction operation they will learn for the rest of their schooling will rest on this idea. And here is the pitfall. Do not introduce the words numerator and denominator before children understand that the bottom number is a promise of equal pieces. Vocabulary before meaning is the classic trap with fractions. Children will chant numerator and denominator for years without ever understanding what they refer to. Worked example 3. Negative numbers in grade 6. Now move up to a grade 6 classroom. The teacher puts 3 pictures on the board side by side, no captions. The first picture is a thermometer reading minus 15 degrees Celsius with snow in the background. The second picture is a submarine in the deep ocean with a depth gauge reading minus 200 meters. The third picture is a bank statement showing a balance of negative $50. The teacher says, these 3 pictures look nothing alike. A thermometer, a submarine, a bank statement. But mathematics says they are the same kind of thing. Why? The children stare. They talk in pairs. They write one word on a sticky note that captures what the 3 pictures share. They stick the words up. The words are things like below, less, minus, opposite. The teacher now plays a sorting game. She shows 8 everyday situations. 4 naturally need negative numbers. 4 never need them. The naturally negative ones are temperature in a freezer, depth below sea level, owing money, floors below ground. The always positive ones are your height, the number of students in the room, the distance you walked today, the time it takes to run a race. She asks one question. What is different about the yes list? The children figure it out. The yes situations have 2 opposite directions from a 0 point, above and below, O and on, up and down. The no situations only go one way. You cannot have a negative height. You cannot run a race in negative time. You cannot have negative students in the room. The teacher writes the discovery on the board in the children's own language. Negative numbers appear when there are 2 opposite directions from a 0 point. That is it. Not less than nothing, not below zero, not the weird numbers. Two opposite directions from a chosen 0 point. The sign tells us the direction. The digits tell us how far. Now she gives them a scenario. A mountaineer is at 4,200 meters on Annapurna. A diver in the same expedition is exploring a coral wall at minus 85 meters below sea level. The class draws a number line. They mark both positions. They calculate the vertical distance. 4,200 plus 85. 4,285 meters. The negative sign on the diver's position no longer means less than nothing. It means below sea level. The zero is not nothing. The zero is the chosen reference point. Here is what I want you to notice about this lesson. By the time these grade 6 children are asked to compute negative 3 plus 5 equals 2, in the next lesson, they will not be applying a memorized rule. They will be reasoning. They have already accepted that negative numbers describe directed quantity. The arithmetic, when it comes, takes half the time it usually does. Because the meaning came first. The pitfall here. Do not introduce operations with negatives in this lesson. The goal here is meaning, not arithmetic. If you rush to negative 3 plus 5, the children memorize a rule before they understand what negatives represent. Resist. The arithmetic can wait. Worked. Example 4. The answer is 42. Now we come back to the grade 7 class we started with. Let me tell you what happened after the wall filled with sticky notes. The teacher drew 4 columns on the board. ADD, multiply, mixed, and sequence. She said, sort your sticky notes into these columns. Move them, stand up. The children physically moved their notes. The ADD column filled with things like 40 plus 2 and 100 minus 58. The multiply column filled with 6 times 7 and 21 times 2. The mixed column had things like 6 times 7 plus 0. The sequence column had things like the 7th even number. The teacher pointed at the columns and said, different rules, same output. Each rule is a recipe. Take an input, apply a consistent operation, get an output. That is a function. A function is not a number. A function is a rule. She wrote one sentence on the board. A function is a rule that takes any input and gives exactly one output. Then she paired the children up. Each pair picked 2 rules from the wall. They built tables of values. For add 35, they got 36, 37, 38, 39, 40, 41, 42. For multiply by 6, they got 6, 12, 18, 24, 30, 36, 42. Then she said, look at how the output changes. As the input goes up by 1 each time, what stays constant? The children noticed. In the add 35 table, the output goes up by 1 each step. In the multiply by 6 table, the output goes up by 6 each step. The teacher said, try one more. Build a table for the rule, square the input. They built it. 1, 4, 9, 16, 25, 36, 49. The output goes up by 3, then 5, then 7, then 9, then 11, then 13. It does not go up by a constant amount. The children gasped. There was an audible gasp in the classroom. The teacher waited. She said, that is the difference. Some functions add a constant amount per step. We have a word for them. They are called linear functions. The graph of a linear function is a straight line. The amount it adds per step has a name. We call it the slope. Notice what just happened. Slope was not defined first. Slope was discovered. The children built tables, noticed the pattern, named the pattern. Then the teacher gave the formal word. Slope is the name of the constant change per step that the children had already seen with their own eyes. Now she gave them a transfer task. A phone plan, $8 per month base fee, 5 cents per minute of calls. Write the function. Build the table. Is it linear? Justify. Solve for a monthly bill of $25.50. The children wrote B equals 0.05 m plus 8. They tabulated. They noticed the bill goes up by $5 every 100 minutes. A constant rate, therefore linear. They solved m equals 350 minutes. By the end of the lesson, these 12-year-olds had discovered functions. Linearity, constant rate of change, slope, y-intercept, and they had applied it to a real-world problem. None of them had been shown. The pitfall in this lesson. Do not write y equals mx plus c on the board before the children have noticed constant change for themselves. If they see the formula first, they memorize it without ever feeling what constant rate of change means. The formula should be the summary of the generalization, not its source. A word about the diploma years. You might be wondering whether this approach is only for younger learners. It is not. Concept-based inquiry deepens rather than thins as the maths becomes more advanced. Take calculus. The traditional approach is to define the derivative as a limit, hand the student a set of differentiation rules, and drill them on procedures. Students learn to take derivatives. They cannot tell you what a derivative means. The CBI approach starts with one rich graph, a velocity time graph of a car journey. The teacher asks two questions that look unrelated. 1. How fast was the car accelerating at minute 4? 2. How far did the car travel in total? The students discover that the first question is read off the gradient of the graph. The second question is read off the area under the graph. Gradient is rate. Area is accumulation. Rate is the derivative. Accumulation is the integral. And then the lesson's punchline. These two operations are inverses of each other. If velocity is the derivative of position, then position is the integral of velocity. They undo each other. That is the fundamental theorem of calculus. Not as a manipulation rule, but as a relationship students have seen with their own eyes on a single graph. It works at every level. The principle does not change. Pattern first, formula after, meaning before notation. The pedagogical heart of CBI maths. If I had to name the single move that makes concept-based inquiry maths work, it would be this. The children articulate the rule in their own words before the teacher writes the formal notation. That is the discipline. That is the work. That is the part you have to practice as a teacher. Because the urge to jump to the formula is strong. The textbook puts the formula first. The exam will test the formula. The other teachers in your school are writing the formula on the board. You feel the pressure to do the same. Resist, wait. Let the children build tables. Let them notice patterns. Let them try to articulate. Let them get it almost right. Let them refine. Let them sometimes get it wrong. Let them argue. Only when they have produced something like the rule in their own mouths do you write the formal symbols. When you do this, two things happen. First, the children walk out understanding mathematics. Not just doing mathematics. They understand it. They know why the formula looks the way it looks. They know what it means. They know when it applies and when it does not. Second, the children walk out believing they can do this. They have done it. The notation came from inside their thinking. They are not consumers of mathematics handed down to them. They are mathematicians. I want to give you one phrase to carry into Monday morning. Here it is. The formula is a summary of an insight, not the source of it. When you write the formula first, you skip the insight. The children have no idea what the formula is summarizing. They memorize, they calculate, they forget. When you let the insight come first, the formula becomes a label for something the children already understand. They do not have to memorize it. They will reconstruct it if they forget it. Because the meaning sits underneath the symbols. The action you can take tomorrow. Here is the single move I want you to try in your next maths lesson. It does not matter what age you teach. It does not matter what topic you are on. Do not write the formula or the algorithm first. Show the pattern, show the data, show the situation, the 47 buttons, the 2 pizzas, the 3 pictures of a thermometer, a submarine, and a bank statement, the number 42 on an empty board. Whatever the topic, find a way to put the pattern in front of the children before you put the rule. Wait, be patient. Let the children look, let them count, let them group, let them sort, let them argue, let them articulate the rule in their own words. Not your words, their words. The first try will be clumsy. The second try will be sharper. By the third or fourth try, in pairs, in whole class share, they will say something close to the formal rule. Only then do you formalize. You write the notation. You introduce the technical word. You say, mathematicians have a name for this. They call it slope, or denominator, or directed quantity, or function. You give them the word as a gift, not as a starting point. That is the move. Pattern first, articulation second, formula third. If you do this once a week, your students will change, not just their test scores, their relationship with mathematics. They will start to believe that mathematics is something you discover, not something you receive. They will start to ask why. They will start to spot patterns in the world outside your classroom and bring them in. And when they leave you, the mathematics they take with them will be the kind that survives. A 60-second recap. We started with a teacher who wrote one number on the board, 42, and asked the class to write the question. We watched her and 3 other teachers across the grades do the same essential move. Pattern first, articulation second, formula third. Place value emerged from 47 messy buttons. Fractions emerged from 2 pizzas and 3 hungry children. Negative numbers emerged from 3 pictures that looked nothing alike but shared an underlying structure. Linear functions emerged from a wall of sticky notes. Calculus emerged from a single velocity time graph. The single piece of advice I want to leave you with is this. The formula is a summary of an insight, not the source of it. Let the insight come first. Always. In chapter 15, we move from mathematics to the sciences. We will start with 2 cans of soda that look identical and watch one sink while the other floats. From that single moment, an entire physics lesson unfolds. From that single moment, the principle of teaching science through phenomena rather than definitions becomes visible. Bring the same curiosity. Get ready to gasp.